Alright, what we want to look at today are limits at infinity, and what we mean by that is, say a graph like this where we have a function that just kind of flattens out, it looks like. We define these as a horizontal asymptote, and pretty much that's the way you want to be looking at these. Is limits at infinity really just means when do I have a horizontal asymptote, or maybe I don't have any horizontal asymptotes. P-T-O-T-E. How if I could spell it today? Horizontal asymptotes here. So in this function, what we're looking at happening here is as we go away towards either negative infinity. So if x is, we'll say, decreasing without any boundary. So it's getting smaller and smaller and smaller. What's happening to the graph? Well, as you can see, we're getting really, really close to this number 3, but we're not going to quite touch it. So we're saying that the function is approaching the value of 3. And I can say the same in the other direction. As x is increasing without bound, I can say, well, then that means here that the function f of x is getting bigger in this case, and it's approaching, I can see in this table, it's approaching again the value of 3. So that's just pretty much what's going to happen, is that if you have something where the limit as x approaches infinity is some number, so in this case the limit is 3, that means this right here, this number 3, that is your horizontal asymptote for these functions. So let's see what this looks like. If I have here the limit of 4 plus 3x, and I want to say the limit as x approaches infinity, well, really, I'm going to just plug in infinity, because I can do that. I can plug in 3 times infinity. Well, infinity times any number is still just infinity. If I add 4 to infinity, it's still just infinity. This limit is infinity as a result. And this should make sense. This is a line, 4 plus 3x. If I have a line here with a positive slope, where do you think it's going to go? It's going to keep going up forever, so that's going to be a limit as you get much, much bigger. Your infinite limit at infinity, is infinity. Now this one, 4 plus 3 over x. Well, I'm going to do the same thing. I'm going to plug in 4 plus 3 over infinity. Now, here I was multiplying by infinity, it still was infinity, multiplying by a big, huge number. Over here, if I'm dividing by a big, huge number, so if I do like 3 divided by 10, or then try 100, or then try 1,000, then 1,000,000, my number's going to keep getting smaller and smaller and smaller. That means this is going to end up being 0. Anything when you divide by infinity is always going to be 0. So my limit is just 4 plus 0, which is 4. Now this idea of dividing by infinity builds into what we have next in terms of finding asymptotes when we do these rational equations. So let's focus on these first 3 at the top. The only difference between them is this right here. What is the power of the top versus the bottom? And we kind of briefly explained this in one of our earlier lessons, but here's the deal. We need to ask ourselves this question. Which is growing faster? And what I mean by that is which one, the top or the bottom in each of these, is going to be increasing at a bigger rate. So, for example, if I'm to plug in here, if I have a big, huge number on the top and a big, huge number squared on the bottom, well, what's going to increase more rapidly? Well, if I take a big number and square it, that's going to increase a lot more rapidly. This is going to increase faster because it's x squared versus just a single x. In this one over here, I have the top x cubed over x squared. So, of course, this one is going to increase faster in that case. In this one, they're the exact same. So we're kind of thinking that they're both going to increase at the same rate. And here's what happens. If the bottom is increasing quicker than the top, that means that essentially I'm going to have some number over a bigger number. And what that means is if I take a number divided by a bigger number, and as these numbers go towards infinity, that's like saying I have infinity over infinity squared. Well, infinity squared is a lot quicker, and it's like we said in the last piece. If I'm dividing by infinity, this is almost like saying I can cancel out an infinity and get 1 over infinity. That's a very improper way, just a very informal way, but essentially the bottom is going to increase faster. Therefore, I'm taking 1 divided by a big number. When that happens, always, 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 my limit is 0. That means my horizontal asymptote is at 0. And this third one, where I have the bigger number on top, the top is increasing faster. This is like I'm saying I have infinity cubed over infinity squared. Which is increasing faster? Well, x cubed is going to keep increasing a lot quicker. So this is going to go up a lot faster. That means my answer here is just going to be positive infinity. There is no horizontal asymptote when I have a limit of infinity. Now, the middle one, this is the tough one because you are increasing at the exact same rate, so we need to pay attention here. The only thing that you can do when they increase at the same rate, we look at the coefficients out in front. My limit here is always just equal to that coefficient. Now, it doesn't matter if I have more terms after this, if I have like an x here and no x is there. All that matters is the degree of the highest term, the highest degree in those polynomials. So, if we look at the bottom, the only difference now between the top and the bottom is that now we're looking at negative infinities for all of these. Negative infinity for each and every one. Okay? In this case, we still are going to have it increasing bigger on the bottom than on the top. That means I still have a horizontal asymptote of 0. In this one right here, I still have, in this case, I'm still going to be looking at this fraction right here, 2 divided by 3. And here's what's happening. Instead of having, essentially this was infinity squared over infinity squared, that would just go away equally. Same here, negative infinity squared over negative infinity squared. Well, the infinities still go away, and my negative signs, whether, no matter what happens there, they're all going to go away. So nothing changes. My limit here is still 2/3. This is the one that could potentially be an issue. And what we need to look at is I have negative infinity cubed over negative infinity squared. My issue is what sign am I going to have? Well, when I have something cubed, it's going to be negative. When I have something squared, it's going to be positive. So the top is still increasing quicker, so it's still infinity. However, negative divided by positive means this limit is going to be negative infinity. So, steps you should look at. Look at the degree. If the degree of the top is less than the degree of the bottom, then we're going to say that our limit is 0, the limit as we approach infinity. If the degree of the top is equal to the degree of the bottom, then we're going to say our limit, is equal to we're going to say the ratio of the coefficients. The ratio of the coefficients. And then the last one is if the degree of the top is bigger than the degree of the bottom, that means the top is increasing bigger than the bottom. That means my limit is going to be either positive or negative infinity. You need to say, based on what the function is and where negatives could have popped up, whether it's going to be infinity or negative infinity. Now, to see what a couple more examples of how these will work. Okay? Limit of sine of x as I approach infinity. So, if I plug in infinity, do I know what sine of infinity is? No, it's some number. But here's the thing. Sine always goes between what two numbers? -1 and 1. So this graph is just always going back and forth forever. I can't say any limit because it's going to keep oscillating. So this is a limit that does not exist because it keeps on oscillating. Now in this case though, I still have sine of x up top, meaning that's going between -1 and 1, but x here is going to keep increasing. So whatever I have some number, but I'm going to keep dividing it by this big, huge number. Well, when I divided by a bigger number, when I divided by infinity, that meant my limit ended up being 0 as a result. Another example here, the limit of x to the 5th is what I'm going to have here. So if I plug in infinity to the 5th, that's just a big, huge number, that is infinity. Here's another example when it was negative infinity to the 5th. Well, 5 negatives, that means I'm going to end up with a negative answer, negative infinity, as my final response. So mainly, remember these rules, wrong direction, remember these rules and just look at what the coefficients are and look at what the negative signs may or may not have. And what do I mean by watch the signs? Well, here's what I'm saying here. First, look at the degrees. The degree of the top is bigger than the bottom, so that means that I'm going to have it increasing faster on top, so I'm going to have infinity. Now, however, when I plug in here, I'm going to have positive numbers down on the bottom. On the top, though, I'm going to end up with infinity cubed, but I want the negative of that. So I will get a negative answer there. That's why that limit there is negative infinity. Likewise, if I did the same one, so let's go to negative infinity now. So negative x cubed over x squared plus x. Okay, same idea. What's going to happen? Top is still bigger than the bottom, so it's still infinity. The question is now, when I have negative infinity cubed, that's going to be a negative, but we still have the negative out in front of it. So negative of a negative will become positive. And on the bottom here, what takes precedent is the x squared. A negative squared is going to be a positive. That's why positives and positives, that's why that's positive infinity. Best thing to do is to take your time and do as many practice problems with these as you can. Good luck. Have a good day.